Hello, everybody. I think we can start now. It's my great pleasure to welcome you to this edition of the Young Earth System Scientists Community Science webinars. But before we get started on this very exciting presentation, just let me go through a quick set of code of conduct for this webinar series. So first of all, please be polite and respectful to the speaker and all the other participants. That's how we can nicely work together. Please keep muted and close the video during the presentation. And please type your questions in the chat box and or in the Q&A tool. And we will record all the contents, the presentation, and all the messages. And while I'm sure everybody is not meanwhile already used to using chat boxes and Q&A tools, don't forget to type your questions there. So now let's get started. It's my great pleasure to introduce and to welcome Professor Louisa Ickes. Louisa Ickes has a PhD in atmospheric physics from Zurich in Switzerland on the topic of clouds. After that, she did a postdoc at the Karlsruhe Institute of Technology in Germany and at the Stockholm University in Sweden. And that included also a trip to the Arctic, still working on clouds, but now focusing on the Arctic, where she will take us today. And after that, she has been working as a junior professional officer at the World Meteorological Organization, to become then an assistant professor at Chalmers University of Technology in Sweden. So, and today the topic she will make us learn about is why do we care about the Arctic and polar bears, on the role of the Arctic climate in our Earth system. So I look very much forward to this, and please, Dr. Ickes, the floor is yours.
Thank you for the introduction, Claudia. So yeah, I'm very excited to take you to the Arctic today, and I hope you learn something about this very fascinating area of our world. I'll start just to explain you what is actually meant by the Arctic, and that's actually a bit funny because there are quite a lot of different definitions about the Arctic. So many people define the Arctic as a region within the Arctic circle, that is this blue dashed line that you can see here, and that marks the latitude above which you don't have any sunset after on solstice, or in winter you don't get any sunrise in this area. But this is a very, you can see like it's a very kind of more a very not so clearly defined line when it comes to actually the Earth system and what we are interested in. So other definitions that you can use is the red line that you can see here that is wobbling a bit around the Arctic Circle, and that is a climate definition of the Arctic, where you define it as the area where you have a 10-degree isotherm in July. So everything which is lower than 10 degrees in July is the Arctic. And then you can also define it based on the vegetation. So that is the green line that you can see here, and that is the definition which is based on the tree line. And then another one which I didn't include because that's a bit more variable is a definition where the Arctic is based on sea ice. And yeah, well, I mean, for my presentation, it doesn't matter too much, but just to say, when I talk about the Arctic, I mostly refer to this area, north, kind of the sea ice area, and quite often like the pictures that you can see and such, they're from the high Arctic, so somewhere here around the North Pole. It may matter if you think about like different countries, they are included in the Arctic or not, and so on, like that might be of importance sometimes. But yeah, I thought, I'll take you today to this fascinating region where normally the only species that you can find there is looking like this. So here you can see a polar bear, which is very curious about all the instrumentation on ice that we had on the expedition where I went. And I thought we just start with looking at actually how is the climate in the Arctic. And to do so, I actually want to know what you think, or if you have an idea about that. So I prepared a quiz for you. So here you can see 6 different climate diagrams that are hydrothermal diagrams. So you can see monthly mean temperature throughout the year and the accumulated monthly precipitation throughout the year. And the diagrams that you can see here are for 6 different places. And one of them is an Arctic place, Longyearbyen in Spitsbergen. And the other ones are not Arctic, but maybe have some kind of, yeah, you will see, in close relation to it. So what we will do, I will just start. Yeah, I think I have to. Yeah, here. Sorry. I start the poll. Hopefully it was plopping up at your screen now. No, I still have to launch. Okay. So now you should see it. And then you can see that each climate diagram has a number, and you can try to think about which place is actually the place that you can see on this climate diagram. And yeah, I leave you a few minutes to try to figure that out. Okay, so sorry for the last people who did not manage on time, but I'll just show you the results. I hope you can see the results, but as I can see, it's quite scattered. So we will look at the solutions, and I explain you what I would look at if I would be asked this question. And so you can see maybe if you look at the climate diagrams that one thing which is significantly different between all of them is the precipitation. Now I can share the poll results. Share results, sorry. Okay, now you can see the results, I'm sorry. And here you can see actually also the solutions. So I cannot see the results anymore. Well, it doesn't matter. So what you can see, as I said, that the precipitation is quite different. So you could see that we have like 2 places. One is Arctic and one is Antarctic. So we would assume that these 2 are rather similar, and actually in both places, the Arctic and the Antarctic, there's not so much precipitation. So if we just look at the precipitation, I would say it should have been one of these 2 diagrams if you want to find the Arctic one. So one of the 2 that doesn't have so much precipitation. Then another thing you could, of course, also look at is the temperature. So it was probably quite clear that the climate diagram number 3, where we have a temperature which is nearly always above 0 degree, is not the Arctic climate diagrams, that is Leipzig. And then the other one, which is also quite high in terms of temperatures, is the one at Reykjavik. That is actually quite close to the Arctic, when you remember the map that I showed in the beginning, but it's just out of the Arctic. And one thing why it's so warm here is because we have the Gulf Stream that is just passing by there. Okay, so we kind of exclude these 2. We are left with these 2 that we assume are maybe the Arctic. Then if you look at the temperatures of the last 2, you can see that this one place has like a very variable temperature over the year, and that is actually this Russian place. So you could assume when the temperature is going from like -40 up to 10 degrees that it's probably a continental place. So that's why you could maybe have excluded that as well. And then Chamdo, the Tibetan place, that doesn't look too bad from the temperatures, but as I said before, it has a lot of precipitation, which is unlikely for the Arctic. Okay, so we are left with these 2 if we want to decide. And there was one thing which was maybe a bit mean, but if you look here at the month, you can see that the upper climate diagram is at the southern hemisphere, while the lower one is at the northern hemisphere. So this one would have been the right one. Here you can see them also a bit how they are placed on the map, and as I said before, so the differences are the precipitation are very different depending on the places and also the temperatures. So if we look at the overview of the Arctic climate, so that is now some statistics for Longyearbyen, that is, I can maybe quickly show it on the map for the ones which are not so aware of it. So that is here, this kind of, this place we are looking at. So that's already quite close to the sea ice edge, and that's a most northern populated place you can find on Earth. So that's why it's a bit easier to find climate data from there compared to other places. As I said, you have in general quite low temperatures. The average temperature is around -5 degrees. It's a very dry place. And the humidity is highest in summer because there you have open ocean instead of sea ice. In winter, it's very dry because you have the sea ice is kind of locking off this water source that you normally have if you have an ocean or a lake or something around. And it's also very cold. That's why we have this very dry conditions. The precipitation is very variable. At this place, the more higher you go up into the ice, the less precipitation you get. And also the wind is quite variable. But yeah, as I said, as you can see with the precipitation, average 7 days a month, that's not so much. Then some things which are specific for the Arctic is the ice cover or sea ice. So there's always some areas covered with sea ice and some parts of the year where you always can find sea ice. And the maximum is in March, and then the minimum you have in September. The albedo, so the amount of the reflective characteristics of the surface, so how much solar radiation is actually reflected by the surface, is very, sorry, now I said it the wrong way around. It's, it's very high, but in summer, of course, it's very low because we don't have this white ice surface. And then the sunshine, so you have half a year, you have 24 hours of light, and the other half a year you have no light at all, so you have night. To come to the question why it's actually so cold up there. So if we think of the Earth in a very simple model, like assuming it's a kind of a cube around the circulating around the sun, half of the Earth is always getting light and the other half doesn't get light. So that's how it would look like in a very simplistic view. But of course, the Earth is not a cube. So we have like a sphere, and that means that the amount of energy that is projected on the Earth's surface, that depends on where you are on this kind of sphere. So if you are somewhere here up on close to the poles, the amount of energy that is coming from the sun is spread over a larger area. So we get less energy up there. Another point is, of course, that we have like kind of tilted sphere going around the sun. So that is as well leading to this kind of inequality in light and non-light, depending on where you are. You can see that here. I'm sorry, it has a bit of a German legend around, but it doesn't matter, I think. So what you can see here on this figure is how much light and non-light you get on different, depending on where you are. And the first column here, that is the North Pole. And there you can see, as I said before, that you have some months where you get like 24 hours of light and some months where you don't get any light. That is one point, but now you could ask, well, but I mean, we saw this climate diagram from the Arctic and we saw the one from the Antarctic. And if you compare the two, and if you ignore that one is on the southern and one is on the northern hemisphere, you can see that there's still quite a difference in temperature. So the one for the Antarctic, which is the one up here, has a lot lower temperatures than the Arctic. And why is that actually the case? So what else is so special about the Arctic is that we have sea ice instead of land. And the sea ice is melting in summer. And that means instead of, sorry, instead of a white surface, we have the ocean water. And the ocean is quite dark. So if you think about like how the Earth looks from above, like from space or something, you can see that the oceans are more or less like black, dark blue areas. And that means they can absorb all the radiation that is coming in that months where the radiation or the solar radiation is actually coming to the Arctic. And that means it can also heat up the whole system and leads to higher temperatures in the summer. So that's why you have quite a difference here in the summer months. Then there are a lot of feedbacks involved as well. So one is connected to the sea ice. I will talk about that later. And then another point is that you have a lot of heat transport into the Arctic due to the ocean currents and also the atmospheric circulation. And that you don't have when you look at the Antarctic. And one reason is that is also related to the sea ice versus land factor. So, I mean, the Antarctic is kind of a land mass. And you can think of a mountain and like wind. How's the wind going when there's a mountain in the way? And normally it's floating around the mountain. So that's why around the Antarctic, we have this kind of very strong wind circulation, which is just like floating around the whole pole. And that prevents everything from coming in or out kind of the Antarctic. So it's a kind of like a barrier. There's also some height differences, of course. I mean, in the Arctic, you're at sea level because you have sea ice and not so much else. And at the Antarctic, you also can be a bit higher up, which makes it also a bit colder because the temperature is decreasing the higher you go up. Yeah. And so how does a typical year looks like in the Arctic? I mean, I said it already that you have a kind of no light in winter. And even if you have a bit of light that is maybe coming, like would maybe come there, it's 70 to 90% that is reflected of all the ice and the snow that you have there. So it's not really staying in there or heating up anything. And the only reason why it's not getting colder and colder and colder in winter is that because there are some kind of warm air flows that come from the European mainland, for example. And January is the coldest month in the Arctic. Then when the spring is starting at the beginning, so there's like slowly some sun coming. And so May is when we have then nearly 24 hours of sun. But in the beginning, not so much is happening because all the sun that is entering the Arctic is reflected because you have all the snow and ice. But then at some areas, especially the one that are closest to land masses, there are like small fractions of the sea ice and the snow slowly melting, and then it's like increasing and decreasing. So in summer then we have like 50% of the sea ice that is kind of lost due to the radiation that enters the Arctic. And the July is then the warmest month. And then in the autumn, well, there's again no light anymore. And that's when the freezing starts again and everything starts to go back into this dark and reflective status of the Arctic. So now I talked a bit about the specifics that we have in the Arctic. Why does it actually matter for us, or what is the role of the Arctic for the rest of the world? I always say the Arctic is the kind of air conditioning or the cooling for the whole world, which I depicted here as ice cream. And what does that actually mean? That means we have a temperature gradient from the equator to the North Pole. So we have a lot of energy that's coming from the sun hitting the equator, and as I showed before, less at the North Pole. And that leads to this general circulation that we have. So the air masses are rising at the equator, and then they're like slowly making their way to the North Pole. And while doing that, they form this three very distinct circulation cells that are called Hadley, Ferrel, and polar cell. And they are also the air, when it's moving from the equator to the North Pole, it's also influenced by the Earth rotation, the Coriolis force, and that's building all the wind systems and the different circulation patterns that we can see. It's not so important to understand that in detail. There's just one thing I wanted to say, and that is here the polar jet. So that is a very, very, very high speed wind that you have, or wind stream, kind of a wind belt that you have in between the ferro cell and the polar cell. And that is coming from this movement, as I explained, from the warm air to the warm region, the equator, where the warm air is like moving its way to the North Pole, and then the Coriolis force, so the rotation of the Earth. And that is leading to this high-speed wind belt. And what does that actually mean, or why is that important? So I depicted it maybe a bit easier here on this figure. So you can see the warm air mass down here. Here's the equator somewhere. And then we have the cold air mass around the North Pole, and the North Pole on the top. And that is this kind of strong wind belt that we have, the polar jet stream. And that is floating around the Earth, like in this direction. But since we have also some, as I said, some rotation of the Earth and other things like mountains and such, it is so that this kind of wind belt is not like a straight belt, it's more like a bit wobbly and so on, and like meandering its way around the Earth. And each of this kind of wobbles that you can see here can then trigger a low or a high pressure system that we have. And yeah, depending on how wobbly it is, or like how fast actually this wind belt is moving, that determines how much of this kind of wobbles you can get. And that is then defining the high and low pressure systems that are laying on the mid-latitudes. And you can see here, for example, that is when we have this kind of very strong wavy structure, and that means that the weather situation can be quite stable. Like you can have this very long persistent or non-long persistent, long persistent low level and high level pressure systems. Yeah, and you normally get the situations which look more stable like this when the temperature gradient is a bit less between the polar and the equator. And that means, we can actually see it in our daily weather, how the temperature or the climate of the Arctic is affecting us. So here you can see a bit more realistic picture of this kind of polar jet. And you can see a weather chart, which is from today, how it looks like above Europe. And here you can see a surface pressure map, where you can see how it relates to the low and high pressure systems. So this kind of strong wobble that we have here, and we have the high pressure system coming from the Azores. So that is one point, but of course it's not only Europe that is affected by the polar climate, it's also the rest of the world. So here you can see it maybe in a bit less Europe focused or a bit more universal picture. So if we have a colder stratosphere, like a colder Arctic, you can see stronger trade winds and more storms. And if you have a less cold stratosphere, you see the weaker trade winds. So it has an influence on the whole world, at least on the northern hemisphere. That's all I wanted to say about the impact of the Arctic weather on our climate. So one could maybe ask now, like, okay, but how does that look like in the future? Of course, I don't really have a crystal ball that is very clever and can tell you how it looks like. But what we can see is that already now a lot of things did change in the Arctic over the recent 100 years or the recent decades. And here in this plot, you can see the temperature increase in the Arctic, or you can actually see a temperature anomaly all over the world. And you can see that the temperature is increasing a lot more in the Arctic or here in the northern areas than everywhere else in the world. And that could also be seen when you look a bit at the sea ice. So here you can see the sea ice extent, how it was actually just now in August 2020. And you can also see another plot where you can see the anomaly of the sea ice compared to, no, I didn't write that down, sorry. I think it's, the reference here was, I think, 60s or 70s. So what you can see is that there's a lot less, the reference is the median from 81 to 2010 is this pink line that you can see here. So there is a lot of sea ice retreat happening in the Arctic due to this increased warming that we have there. Here you can see it a bit easier plot maybe as well. So that is the extent of the Arctic sea ice over the last years. The oldest data set plotted here is from 1979, and then we have 2020 somewhere here. So you can really see that there's a new record of the minimum extent of Arctic sea ice. And that has some implications, especially for the biosphere and everything else, like living up there, which is mostly polar bears. So here you can see one polar bear that is kind of starving because he cannot really find any food anymore, because they mostly eat seals, and the seals, they of course live on ice. So if there's less ice, they are not there anymore. And why is that actually happening like this? So you could see that the temperature is increasing so much more in the Arctic than everywhere else in the world. And there's one reason to that, and that is the phenomena is called Arctic amplification. And the reason for the Arctic amplification is that we have a lot of feedback processes happening in the Arctic. A feedback process is actually a process where something which happens triggers something else, and that enhances that whatever happens, or it doesn't enhance whatever's happening, like the other way around. So if we look at this schematic, we can see that if we have an increase of global surface temperature, and then we have a rise in the temperature at the Earth's surface in the Arctic as well. In this case, so we have larger energy flows, and the upper ocean layer is warming. And what can you find on the upper ocean layer? So as I said before, you have a lot of sea ice in the Arctic. So if the upper ocean layer warms, then you get less sea ice. So the sea ice is melting, also the snow on top of the sea ice. And that means that the solar radiation that comes into the Arctic is reflected less, because you have less of this kind of white surfaces, and a lot of it is more absorbed, and that means it's getting warmer and warmer, and you lose a lot more of the sea ice. It's like this kind of feedback cycle. And it's not only the sea ice, there are also a lot of other things connected to the sea ice. So that the biological activity is different if you have sea ice or if you have the open water. And that is triggering like everything which comes into the air, because normally the sea ice is like a lock of the ocean. If you have no sea ice anymore, then there's a lot that can come actually up into the atmosphere from the ocean, like sea salt particles or small fragments of algae and this kind of things, and that have an effect on the clouds. I will explain that in a minute as well if I still have time for that. We'll see. Yeah, but that is a general feedback process that is happening there. And yeah, I will do that a bit, yeah, shorter. I try at least. So as I said, one piece is kind of connected to this, to the sea ice, and one piece of it is the clouds. And why are the clouds so important in the Arctic? Well, if you have clouds on top of the ocean here, for example, they would reflect the sunlight, and that means that the ocean would heat up less in this case. So maybe then some sea ice can form again. So they're kind of, yeah, acting in the opposite way. And yeah, as I said, they can be influenced by the whole region. So yeah, sorry, just looking at the time, I think I do it a bit quicker. But maybe just to say one thing. So as I said, we lose a lot of sea ice, and that releases or gives the possibility to release of aerosol particles like marine organics or like marine fragments. And that can then influence the cloud structure, because if you look inside such a cloud that we typically have over the Arctic, it contains very often of cloud particles and ice crystals at the same time. And these ice crystals, in these clouds, they can only form if they have some aerosol particles, if there's some kind of something the water molecules can kind of attach to and then freeze to ice crystals. And that can come from the oceans or from some kind of transported sources, and that can change quite a lot how these clouds look like. Yeah. But yeah, just to say a few more words, actually, I mean, sorry that this was now a bit fast, but maybe just to say there are a lot of complex mechanism that happens in the Arctic, and how do we actually try to solve that, or how do we actually try to understand these processes better? And there are two different yeah, approaches one can use. One of them is to do measurements, of course. So there are a lot of in situ campaigns happening in the Arctic where people actually go there and try to make different kind of measurements and try to figure out some of the processes that I just explained. You can also use remote sensing, so different kind of satellites and satellite products that can also help to understand what is happening. Sometimes a bit tricky, for example, if you want to study clouds and they are above the ice, like if you look from on it from above, you just see white, so it's very difficult to see where's actually a cloud and where's the ice. But it depends a bit what you want to study, of course. And then another approach is to do modeling, so you can either work with an Earth system or a global climate model to study how the flows and everything are affected by the temperature in the Arctic. Or you can use small scale models like which is depicted here, where you can really try to understand how one cloud or something like that is forming in the Arctic. Yeah. And yeah, I think time-wise, yes, I'm coming to the summary. So I did show you how the climate looks like in the Arctic and what makes it so special. So we talked a bit about this kind of temperature curve and the precipitation compared to other places in the Earth. I did also explain you that the temperature gradient, like the difference of temperature that you have in between the equator and the pole or the Arctic, is actually driving the circulation patterns that we have on Earth. And one part of this is this kind of polar jet stream that is defining the weather in Europe and everywhere else. And then I also talked about that the Arctic is actually changing quite a lot during the recent years. So there's an amplified increase in temperature, and there's also loss of sea ice over the recent years. And that is why we try to understand all the feedback processes and everything that is happening in the Arctic like, yeah, for example, this cloud coupling that I only shortly mentioned. But yeah. And I think now it's time for questions, if there are any.
Thank you very much for these very interesting insights and to see again how everything is connected and the many impacts it has. Very nice overview. And there's already a question from Adriana asking if the nucleation centers can be cosmic rays.
Yeah, so there was one theory looking at the influence of cosmic rays on clouds, not so much focused actually on the Arctic, I think. I mean, they were more looking over like in all different kind of places. If I recall correctly from the recent studies that have been done in this kind of topic, is that they did show that it doesn't have such a strong influence, like because most of the times the nucleation is more triggered by different organics that you have in the atmosphere, and it would only be important if you don't have any of these, but normally they're still, some are always around. So
Thank you. And we just get the next question. Thanking you a lot for your presentation and also having learned a lot about the Arctic. Marisol would like to know how well the CMAP model simulates the Arctic amplification.
It got better now with the newest set of the CMAP 5 models. The generation before, like CMAP 3, they had a lot of problems to see the Arctic amplification, and that was mostly related to the sea ice modules. So the newest generation of climate models that are taking part in CMAP 5 or the newest, the now soon to become scenarios, they have a more sophisticated sea ice model than they had before, so they can better actually simulate this process that is happening. And before they were very often using like only constant sea ice field, and then they couldn't really see this process. So maybe to say it short, it's getting better.
Thank you. And now Mariano would like to know if climate feedbacks affect the formation or no formation of sea ice in the Arctic, or do they also affect the thickness of sea ice? And what is the average thickness of sea ice in the Arctic?
Ooh. Not sure if I can answer the last one. Yeah, so they influence as well the formation and like the melting and like freezing again of sea ice, but also the thickness, of course. I think the thickness should be like, it depends how old the ice is. I think like, I mean, like newer sea ice, that's maybe around a meter or so that's not so thick. And then the sea ice, which is a bit older, should be around 3 meters. But yeah, I would not fully trust these answers, so maybe check it again, but that's what I remember at least.
And do you think it is still possible to avoid climate catastrophe? Asked Agnieszka.
That is a very difficult question, I would say. I mean, that is what you're trying to simulate with different climate models. And the problem there is always that you have to make a lot of assumptions, like how much energy are we using in like 10 or up to 100 years, how much greenhouse gases do we emit, and so on. So it's quite difficult to answer. I'm not sure, Claudia, you want to comment on that?
Well, it all depends on the choices that will be taken in the next years. So there, it would be my answer to that question.
Yeah.
And the next question is, what is the state of greenhouse gases in the Arctic?
Ooh. That I actually don't know, I think. Yeah. Yeah, sorry, I have to pass on that.
And another question is, do stratospheric clouds also play a role on Arctic feedbacks?
There are some which can play a role, but it's mostly like not in terms of the feedback that I explained with the sea ice and like having an influence on the temperature, but there are a lot of feedback processes that happen in terms of ozone reduction, like the ozone hole that you can see in the Arctic. I mean, luckily it's not so strong anymore as it was, but so there are some processes that happen in this kind of polar stratospheric clouds that kind of help, or not help us, maybe enhance the decrease of ozone. But for the, if you look at the radiation balance, they're not so important as the other ones, or at least the lower clouds are more persistent there.
And do you know if the last fires in the US are already impacting the Arctic?
Oh, that's a good question. I think up by now, the air, I know that some people saw already some of the particles that came up from this wildfires. I know some people doing measurements in Vancouver, and they also looked a bit higher north. So if you look at the Canadian Arctic, there should be a lot of particles that made its way up there. So yeah, I think you can see them, how much influence it has whatsoever. I mean, that's a bit difficult to say right now, but I mean, in general, what is happening when you have like such big wildfires is that, for example, all these particles, they sediment on the snow or on the ice. So you can imagine you have this kind of black particles that are kind of like falling down on the snow. And the effect that you get there then is that the black particles, they can absorb all the radiation that comes there. And so the snow, so if you have a snow field that has a lot of like ash on top, like a lot of these soot particles, this snow field will absorb a lot more of the solar radiation. So it can lead to a melting of this snow field compared to a snow field where you don't have any ash on top. But I guess you would need to analyze that in one year or something. Yeah.
Thank you. So many interesting questions. The next one would be, did the ozone hole formed in the Arctic earlier this year affect sea ice? Do we already know something about this?
Not that I know. Let's say it like this. Yeah.
Probably needs a bit more time to answer that question, to analyze the data in detail, but it's a very good question.
Yeah.
And the next question is, what kind of clouds reflect solar radiation back, and what kind of cloud enhances radiation?
Yeah, I mean, that really depends on the area where you are. So in the Arctic, the clouds that are most important are the clouds that I also did show on this kind of sketch that I had. So that are the mixed phase clouds, where you have water droplets and ice crystals, and they are more this kind of lower clouds. And they are in the Arctic, they're very often warmer than the surface, because the surface, it's kind of, you have this warm, moist air coming into the Arctic from, for example, Europe. And then you have this clouds forming, and the air floating over the sea ice is of course cooled down. So the clouds are a bit warmer than the surface. And that means they emit more like higher temperature radiation than the surface. And that means they cool down the surface.
Okay, thank you. That were a lot of very interesting and very challenging questions, but that makes them even better questions.
Yeah.
So I think we can now thank you very much, Dr. Ickes, for your presentation and for answering the questions. and for sharing your insights on the Arctic with us today. And I would now also like to draw your attention to our next webinar in the Science Webinar Series, which will be on 8th October at 1 p.m. UTC again. The speaker will be Juan Rivera from Argentina, and he will talk about water resources change in central western Argentina under the Paris Agreement warming targets. So I hope you will join us all again for that.
Thank you all for listening. Sorry.
Thank you for listening. And in the chat, you just got the link to register to the next one. And thank you also all for coming and for all your great interaction and your really good questions, which made it a lot of fun.
And thank you, Claudia and Valentina, for inviting me. It was a fun activity.
Thank you, Luisa. Bye, everyone. See you on October 8th for the ones who wants to join one presentation. Okay, and this presentation will be uploaded on YouTube in the upcoming days. So, bye.